This presentation covers the basic concepts underlying performance comparisons of programs. Runtimes of programs will typically vary. Keep in mind, programs can either be deterministic programs, that means given a set of inputs, they execute the same set of instructions to provide the same output, or they could be non-deterministic because they have some random number generators or some stochastic processes that they are modeling. Immaterial of the type of program that's being run, runtimes on modern programs on modern computers will vary a lot. This is because on a modern computer, there are many tasks or processes that are running, and the operating system does preemptive multitasking, and context switching can introduce randomness in the timings of programs. In addition, depending on the hardware and the CPU, the caching and cache behaviors can vary, and caching can introduce a lot of variance in the runtime of programs. Furthermore, other hardware characteristics like response times of I/O devices or other devices that the program may be using can introduce variance or changes in the runtime of the program. So the real question that we are trying to answer is, given that runtimes of programs can vary a lot, how can we effectively compare the performance of two different types of programs or two different runs of the same program? And the answer is to use what is known as statistical confidence intervals. A confidence interval basically indicates a range of values that the actual observation will lie within some probability. So for example, let's say we have a 95% confidence interval of 5.2 seconds to 7.3 seconds for the runtime of a given program. This confidence interval essentially indicates that if 100 runtimes are measured, then 95 of those observations will lie in this range, and the reason for the 95 is it's a 95% confidence interval. Typically, runtimes of programs are always reported as a mean plus or minus a confidence interval. So for example, a runtime of 5 plus or minus 1.25 seconds would result in a range which is 4.75 to 6.25 seconds for the program. So that means every time the program is run, there's a 95% chance that the runtime will be in the range 4.75 to 6.25 seconds. The key thing to keep in mind when computing confidence intervals is sufficient number of samples need to be recorded so that the comparisons and analysis are statistically significant. For example, if too few samples are measured, then there's a significant overlap between the confidence intervals or the measurements of the two programs or two versions of the program. And in this case, more data is necessary before the confidence intervals can be correctly measured and computed. Here, there is somewhat clear separation, but still the number of samples is insufficient to compute a 95% confidence interval. Here is a sufficient number of samples. Sure, there is some overlap, but the separation is statistically significant, so we can draw some conclusions from this data. You can do a lot more sampling, but that doesn't really help. That means it doesn't add a whole lot of clarity. And sometimes it can also be unethical in the sense that you're running these large programs on shared computational clusters, taking time and resources that somebody else could have been using in a more effective manner. So the question then becomes, how do we figure out the number of samples that we need in order to compute a 95% confidence interval? Here, statistics can help if we can make some assumptions. So for example, we have to make some assumptions on the nature or variance in the data, and we have to make some assumptions on how much error that we are willing to accept in the data. So given this kind of a setup, statistics gives us a simple formula to determine n, which is the number of samples that we need. So for example, if in our experiments we assume that the acceptable error margin is about 2 seconds, so that means we're willing to accept an error of 2 seconds. In other words, we assume that the runtime of your benchmark is never less than 2 seconds. And also we assume that the variance in the data is pretty small. That means we accept a variance we expect variance to be less than 2 seconds in every run. That means in order to keep the variance low, we require a lightly loaded or dedicated machine, and this is typically accomplished by using compute nodes on supercomputing clusters. So when you plug in these values, error value E of 2 and a sigma of 2 seconds, then into the formula there, you'll find n to be about 4.8 something, which essentially means that about 5 samples are sufficient to perform this experiment. So for example, if you have 5 samples, that means n is equal to 5, computing confidence intervals from 5 runs of a program is relatively straightforward. First you compute the mean mu, then you compute sigma, the standard deviation, and then you plug in sigma, mu, and n into the formula to compute the 95% confidence interval. Here, the number 2.776 is important because it's been obtained from the student t-distribution table using 4 degrees of freedom. Because n is 5, the degrees of freedom is 4. Once you have the confidence interval, it's important to understand how to interpret those confidence intervals to draw meaningful conclusions from runtime data. For example, if the confidence intervals are clearly separated, then there's a clear difference and the data is sufficient to draw meaningful conclusions. You can now decide that one version is faster or slower when compared to the other. If there's a full overlap and the variance is pretty small, as we expect, then we can safely conclude that there is no difference in the runtimes of the two programs. In other words, they are identical to each other in terms of performance. If there is a partial overlap in the confidence interval and the variance is small, here we can still conclude that there is some difference, but it's not of practical importance. That means the performance of the two versions are sufficiently similar to each other and it would be hard to distinguish between them. But there's another case where there is partial overlap, but the variance is pretty large. So in this case, the range of data is too large and we cannot draw meaningful conclusions from it, and we need more data in order to draw some meaningful conclusion. So you have to run more experiments, collect more data to reduce the variance so that you can then draw meaningful conclusions using a 95% confidence interval. And of course, there are cases where you might have a negative confidence interval. In this case, again, the variance was too large and you need more analysis, or you need to collect more data in order to draw meaningful conclusions. So in all of the experiments that we do, we will be collecting at least 5 runs and using confidence intervals to compare the performance of different benchmarks, micro benchmarks, or configurations of programs.